Again, you could say, well, when I integrate, don't have an arbitrary constant. Remember, you are integrating in such a way to minimize, right? So you kind of take out arbitrary constants. You integrate, has to be a minimum. There it is. Okay? So this is now equivalent to what we had before. It's just a different formulation. Okay? Now, why did I just make my problem harder? You could ask that question. It's a fair question. Kristen, is that good? That's a fair question, right? All right. You could also ask why you ran marathons every year. That's why would you do that? That's just more work.
The second part of this is
yeah.
the boundary condition.
Yes, this is boundary condition. I'm not going to work that one through. I'm just going to say, let's just do one to do the convincing.
So you're setting both, minimizing both of them.
Yeah, you minimize this and minimize that, and then you reproduce everything you have there. Okay. All right, so now, what are we going to do with this? Now, here is the key observation about this. I'll take away this work here. Notice what has happened. Before, I had a term like this. And this term sort of became this. Okay? And this is where you get the huge potential benefit. Let me make clear why you have a huge benefit. This still has two derivatives of u, right? If you do go through, you have, suppose p is constant for a moment. Let's take p out. This is then uxx, and this is ux squared. Here's the big difference. How are we trying to represent the solution? We're trying to represent the solution with things like this. Yeah? And by the way, two derivatives in y do something similar. And if you look at my PDE carries the following information. uxx plus uyy. I have like a Laplacian. Again, supposing p and q are constant, or one in particular. I have this here. And I want to represent my solution with that. But if I put that in there, what happens? This is all 0. However, this effectively becomes does this carry information there? Well, take u of x. I get a b, and I'm going to square it. So this becomes like b squared plus c squared. So my Laplacian has information now if I rewrite it this way in integral form. My Laplacian can handle me using a simplex method. So this is why we did all this work, ultimately. If you miss this piece, bad. So, everybody focused? Everybody focused, right? Focused? This is the key part of the lecture right there. I did all this work for only one reason. To tell you that if you replace two derivatives by one, you get information with a simplex. That's it. This is why when you think about using finite element, it's a pain in the ass. What you're doing is trading out, but it's nice, right? Because, yes, it's a harder equation, but it's really easy elements, right? That's what you're really doing. Say, look, I can use super easy elements as long as I make my equation harder. Okay? You have to pick your poison. If you want to use harder elements, you could stay with your formulation. Okay? All right. Everybody okay with that? Shall we meditate on it for a little while? Okay, good. All right. Everybody good with that? You did yoga this morning, right, Haley? So you're good? Are you feeling calm right now in class? Am I making you too excited in class? Am I raising your blood pressure up? I hope not. Okay, good. I don't want to ruin that yoga high. Okay.
And then get the integral.
Yeah, so what I'm going to do now is, well, let's talk. This is what we're going to do. Now we're going to say, here's my representation. Now what do I do? Okay, here's what you do now. So let's talk about what you're going to do now. All right. So now what I'm going to do is do the following. Actually, I will now represent my solution as a bunch of these simplex elements. U of x, y, as I go around, is going to be a sum of all these little triangles that I put together. Okay? Now, these here are linear. That's what we just wrote down. They're going to be linear, and they're going to be piecewise linear polynomials, right? So this is what we want to do. And these are some constants that I have to determine. We'll talk about how I determine them. So somehow I have to determine both the constants here plus the constants of these linear polynomials all together to represent my solution. Okay? And so these are going to convey the information of not only satisfying the boundary, how do they talk to their neighbors has to be satisfied, and in addition, the PD has to be satisfied. So I have to meet all these constraints. Okay?
Triangle?
Yeah.
Fine. Okay, so it's
So each one of these is one of these little patches. Let me do that. Yeah, well, this is only defined in that patch, and then, right, yeah. So, and then it's not even defined outside of that patch. So you just patch all this together. So now what I'm going to do with this, and by the way, what I got to do is I got to pick these gammas. So let me write this. A certain number of these triangles. A certain number of these triangles are going to hit the boundary. Okay? Let's say that what I have is the interior triangles, gamma 1 through gamma n. This is in the interior. And the triangles that hit the boundary, gamma n plus 1 to gamma n m. Okay? So from our picture over here, these over here that touch the boundaries, these are our boundary triangles. These have like the gamma n plus 1, gamma n plus 2, and so forth. Anybody that touches that boundary has a constraint that they have to satisfy for the boundary. Okay, so those are all triangles on the boundary. However, if you're in the middle, your only constraint is that you got to talk to your neighbor. Okay, and that's not so hard to do. Your information is shared. Okay, but by the way, what was the key about finite difference? What made our matrix structures? If you remember, we spent a long time building those A, B, C matrices that had these interesting shapes, right? These diagonal shapes, because ultimately you got AX equal to B, because if you're at this point in a finite difference scheme and you talk to your two neighbors, you can't solve for yourself, right? Because your neighbors don't know what they are until you solve the whole, right? You have to construct it all the way out to the boundary with boundary information, and to get everybody solved at once, you do AX equal to B. Same thing here. You cannot say, I can solve for myself here. No, it's like, well, I'm touching these triangles, but then they're having positions over here. And when you set the whole thing up, that's where you get your AX equal to B. Then you do backslash if you want. Okay? That's what it's going to come down to. And so let's talk about how do I actually make this big, giant AX equal to B. You know it's going to be big. You know it's going to be giant, right? You know this at this point, right? Okay? So we're going to basically do it by saying, take this and shove it into this. All right. How should I say this? Finite element. You only need to do this once in your life. Right? Once it's done once for this equation, it's done for all time. Like the result is the same, no matter how many times you choose to do it. So people have already done it. People have programmed it up. So it's like, use their way. This is the beauty of one of these canned softwares, is that like this stuff is not that hard. Yeah, by the way, your ability to make a mistake on this is super high. Okay? All right? So, but if someone's programmed it, test bedded it, they know it works, and then you can just give them that, and you're done. Okay? I like that.